Okay. So I would say the other most important algorithm is Gaussian mixture models, which we'll discuss next. But this is a crisp variant. What you do in Kmeans clustering is you optimize the following problem. So you can define an error function. It finds at least a local minimum to this error function. So it looks for each observation I for its closest cluster center. So the cluster centers are additional points that are located in feature space, just like the observation. It locates the closest of these, computes the squared Euclidean distance, and sums that over all observations. Or an alternative way of writing this error function is in terms of a Frobenius distance matrix. Where X is a P by N matrix of the original observations. C is a P by K matrix of cluster centers. So this has the coordinates of the cluster centers. And M is a binary membership matrix. Of dimensions K by N. And is a crisp clustering, so each observation must belong to exactly one cluster center only. So we have so 1 transpose is a vector of ones, and if we multiply from the left with this vector of ones, then we get a 1. So in other words, each observation must belong to a single cluster. Okay, and the user specifies the number k of desired cluster centers, and the procedure then iterates between 2 steps, namely to find the closest cluster center for each observation. And to then move the cluster center or the prototype or the representative of a cluster to the average of its observations. And luckily, this procedure is guaranteed to converge, unfortunately only to a local minimum. show you an example. So we have a 2D feature space, a couple of observations, and 3 cluster centers have been put randomly in this space. So we have 3 cluster centers, and the observations have already been assigned to the closest cluster center. So you see that all of that belongs to that cluster center. And if now we move each cluster to the center of its observations, this one is going to jump way down. This one is probably going to move up a little bit. And let's do that. And if we now ask for each observation to which cluster center it belongs, these ones are going to change allegiance. So these ones will next want to belong to this one. So the red cluster is going to grow larger in this region here. And now we can re-estimate the positions. So this one no longer represents those points, so it's going to move further in that direction. This one's probably going to move a little bit further in that direction. And so on. And then we can iterate this until nothing changes. Yeah, so typically they are put at the, at the position of a random sample from the training set. I think I had initialized them just randomly anywhere in the feature space. So this convergence is guaranteed almost surely, and it corresponds to a Newton optimization of this error function that you've seen. Now this error function, it may remind you of something we've seen before. If we only constrain the rank of these matrices, but do not require that they be binary and stochastic, then the solution would be given by the singular value decomposition or by principal components analysis. So you can look at this as a way of compressing your data, or of a way of reducing the dimensionality of your data with this additional constraint that each point is explained by just a single cluster center. There are a couple of variants. So for instance, the cluster centers here will typically not coincide with any of the observations. Sometimes that is a problem, and there's a method called K-medoid clustering, where the cluster centers are restricted to one of the observations. Then there are an important heuristic improvement is an algorithm called isodata. which can split or merge clusters over time. And that allows you to escape local minima. In particular, if you just initialize your cluster centers randomly in feature space, it may happen that several of the cluster centers get attracted by outliers, and then they explain just those outliers, and they're never going to get away. So let's say we have many, many, many points here, and an outlier there. So we get one cluster center here, one cluster center there, and it's never going to see any of the other points, and hence is not going to be able to move there. On the other hand, that can also be an optimum solution because we're looking at the square of the Euclidean distance here. So if the single observation is sufficiently far from the rest, then it really wants to have its own cluster center. So in that sense, K-means is sensitive to outliers. And well, in ISO data, there are different versions out there, but broadly speaking, it looks for the single cluster center that makes the largest contribution to this error and is going to split this cluster center. Or vice versa, if you have a cluster center that contributes little to the error, then you can try and eliminate this cluster center and see if you still get reasonable results. Then there is the leader-follower algorithm, which is an online version. So you can either use it on the entire data, and it works by letting each new observation attract the closest cluster center a little bit. How much a little exactly is, that has to do with how much memory you want your algorithm to have. There's also a single pass version of this algorithm. In the single pass version, this is perhaps the fastest clustering algorithm around. In a single pass version, you start with a single cluster center, and then you present each new observation in turn, and you find for each observation the closest cluster center. And if it is closer than some threshold, then that observation attracts the cluster center a little bit. But if it's further than some threshold, then this new observation becomes its own new cluster center. So that makes for very fast algorithms. So a single pass version of that exists. And then the algorithm can be used hierarchically. Where you start with a given number of cluster centers and do K-means clustering, and then use a predefined branching factor. So for instance, you can then replace each cluster center by, let's say, 5 new cluster centers. And you have let me draw a tree with just 3. And so on. So you can have, I just want to stress the point that you can have branching factors other than 2 in these trees. And well, that is a crisp method, but it is hierarchical. And this is, so I mentioned this one because K-means clustering was traditionally considered a non-hierarchical algorithm, but it can be made hierarchical in that fashion. And that's also computationally quite efficient. The reason, or the efficiency comes from the fact that typically you have a k much smaller than n. So in the density clustering algorithm that we saw before, you had to compute distances from each observation to all others, and here you just need to compute distances from each cluster center to all observations. So this algorithm was studied in the context of telecommunications and in the context of compression, where it is known under different names. So K-means clustering is the same as the Linde-Buzow-Gray algorithm. From communications, where it was used for vector quantization. Now, where does this word vector quantization come from? Let's assume that you have some continuous variable. This could be the amplitude of the microphone in your telephone. In the old days, when telephones were analogous devices, and well, microphones still are analog devices. So let's say we have some narrow distribution, and we have some minimum and maximum value. So this would be P of x. Now, one way to, if you want to transmit, or if you want to save bandwidth, then rather than transmit the precise value x, you can transmit simply, you can round to some number. So let's say we could partition this into 256 numbers, for instance, and we would then have, as a very simplest compression scheme, we could use rounding. However, if you want to minimize the distortion, so the average squared Euclidean error, then it doesn't make sense to waste so many code vectors in areas with very low density. So it would make more sense to have more code vectors in regions where the density is high. So let me plot the distribution function here. So this would be the integral of minus infinity up to x of this density that we've just seen here. And if we use this rounding, we will just use the same step size everywhere. And this is perfect for a uniform distribution. So just to round is perfect when you have no prior information about the density of your signal. But for a distribution that is more concentrated, it makes more sense to keep your code vectors or to invest more code vectors or to use finer bins in high density regions. So for instance, something like that. So if you now if I now plot the locations of these jumps, of these staircase jumps, I will find more cluster centers or smaller bins in regions of high density. And in one dimension, this is called scalar quantization. And in higher dimensions, well, you will obtain different optimum shapes. So you could say that vector quantization effectively is something like histogramming, but with non-regular bins. So vector quantization approximates an exact measurement or an exact observation with the closest code vector. And the collection of code vectors is the same as cluster centers, is called a code book. And this is essentially something like a histogram with irregular bins. Well, so the histogram really gives you the count. Vector quantization only means that you find the appropriate code vector, but you can then, of course, just like in histogram, you can see how often each code vector was activated. So I'm going to show you a 2D example. This is from a website called datacompression.com. And you see a two-dimensional, so this is now vector quantization, you see a 2D Gaussian density of points, and the effect of this Kmeans or Linde-Buzo-Gray algorithm. And whenever we get convergence, then each of these cluster centers is split into two, and by the mechanism that I have just described, the points then rearrange in space. So this point would now explain all of those observations, that point would explain all of those observations, etc. And again, when convergence is achieved, this is further, each cluster center is partitioned into two. So this gives you a number of vector quantizations at increasingly finer detail. And you will see that if we go to a larger number of cluster centers, in 2 dimensions, we would obtain hexagonal. Now, unfortunately, we start from the beginning. In 2 dimensions, we would find hexagonal bins if the density is locally constant. But the point of this is to consider problems where the density is not constant and to approximate, well, to invest more code vectors in areas where you need, where you're likelier to see some data. So where it's, where it is a better investment, essentially. I have another example, static example. So we see a poorly saturated image. As a human, you would probably see three objects: a predator, the object of desire, and water. And shown here is each pixel or a subset of the pixels in the RGB space. So each pixel has a red, green, and blue value, and each pixel is indicated in this red, green, blue space according to well, its color. And actually, I think the meat is somewhere here. So we have relatively high values for red. The water is there, and the tiger is probably those pixels here. And now, if we want to store this image pixel by pixel, that is a lot of numbers. And you could use vector quantization for compression here by, for instance, using just two cluster centers. So in this case, one cluster center is here and one cluster center is there. And if you look carefully, there are just two colors in those points currently. And well, this would be the resulting clustering. It's not exactly what a human would do, because you see this is seen as part of the water, or it doesn't even know about water. So black is one cluster and green is the other cluster. And notice that green really goes into the predator here. So don't be too disappointed about image processing. We have more sophisticated methods at hand, and we can deal with such problems also. But this is now really the most primitive compression you can do by just looking at the RGB values of each pixel, irrespective of what you have in the surroundings. So this would be two cluster centers. This would be, I guess, 4 cluster centers. And this would be, I think, 20 cluster centers. And here, at least, with this quality of projection, with 20 cluster centers, you already get a pretty good approximation to the original image. Now, real compression methods look especially at the spatial context. So in JPEG compression, for instance, one looks at local neighborhoods, and but even in JPEG compression, because JPEG is a lossy compression, and it is lossy because somewhere in this pipeline vector quantization is hidden. So if you now count, in the sense of the histogram that I mentioned, if you count how often each observation or how often each code vector was activated by an observation that lay closer to this code vector than anything else, you obtain counts, just like in histogram. And these counts are useful for summarizing images. This is sometimes called the bag of words representation. And I will show you an early example. This is from 2001, work by Leung and Malik. And they were looking at different textures and how to discriminate them. And so they span some kind of feature space, does not matter very much which, and then look at the image patch by patch. And each patch is projected into this feature space. And in feature space, you have code vectors. So you have cluster centers that were found by Kmeans clustering. And then you can count for different materials, so plastic, plaster, and so on. You can count for different materials how often each code vector was activated or visited by all the patches from one particular image. And as a result, we get this type of histogram. And these histograms look different for different materials. And these histograms can then be used as input for example, for a nearest neighbor classifier or for a linear support vector machine or similar. So in essence, this is a huge dimension reduction which is achieved here by means of this bag of words or bag of textons representation, by going from a whole image with millions of pixels to a histogram with just 100 bins, a histogram that states how often each cluster center was closest to one of the patches of an image in this given feature space. Is that clear? Do you have questions? What the bars are? Okay. So in the bag of words representation, we need some kind of feature space. The feature space could be, for instance, all the gray values that we have in a given image patch. So let's say if we take a 16 by 16 patch, and if we assume it's a gray value image, we would have 256 gray values for each patch. So each patch lies in a feature space with 256 dimensions. And out of these 256 dimensions, I'm showing only 2 now. Yeah? And we can now have different distributions in this space. So a single patch of, let's say, an image showing a carpet, a single patch would lie here. And the next patch of the carpet would lie here, and the next patch would lie there. But overall, for the carpet class, we get some distribution in this space. So let's say this is for carpet. And then we have images of flowers, and they have a different or the patches that show flowers, they have a different distribution in this space. And we now get, so this we know from a training set. And if we now get an unknown image, we can also put it into this space, and we need to decide if I did a density estimate, I would get this. Now I need to decide, does this image show a carpet or a flower? So as a human, we would say, you know, it looks more like the carpet distribution, but this is where just 2 dimensions, and we really have 256, so we cannot look at these directly. So what is done is the following. A code book is found. A code book of code vectors, or of Kmeans cluster centers. And these code vectors, if I used a naive Cartesian grid, I would just put these code vectors here in a regular pattern in this feature space. But as we discussed before, especially if I do this in 256 dimension, most of the bins would just be empty. So those would be bad code vectors. So instead, I optimize their position using Kmeans. And then I find code vectors in areas of high density, and a few code vectors in areas of low density. And if I now get a given image, I count how often each of these code vectors was activated. So, for example, let's say I have plotted probably 20 bins. There's no ordering among these bins, some random ordering. And for instance, there are some code vectors which are only visited by the carpet class, and other code vectors which are only visited by the flower class, but not by carpet. And then we have a couple of code vectors where we observe both classes. So this entire distribution has now been represented as just a 20-dimensional vector. And this entire distribution has been presented as just that 20-dimensional vector. And if I now obtain a unknown distribution, I also check how often each of the code vectors is visited. And I then need to compare it to my training set. Oh, sorry, I should have used the white color here because we don't know yet what it is. And we now ask, is it more similar to this histogram or more similar to that histogram? And for that, to compare histograms, I could use a chi-squared distance, or I could use, and then use a one nearest neighbor classifier, or I could use a linear support vector machine or similar. So in this case, we would say that this histogram is more similar to that one, and then predict that the image that we've seen is probably a carpet and not flower. So using vector quantization allows us to summarize a very high dimensional distribution in terms of just a single vector of numbers, but this is a lossy compression. Okay, we lose information in this process. More questions? All right. So we have seen a crisp algorithm that is relatively cheap computationally and has a number of favorable properties. And we will, after the break, look at a fuzzy version of that, namely at Gaussian mixture models and at how to optimize them.